applications using E. We are wrapping up this unit with some more story problems. We will revisit some formulas that we have used in the past, but we're going to be solving them for missing variables in the middle and just practicing in general how to solve some equations that use that transcendental number E, irrational number E. So number 1 says Tara's parents invested $5,000 in an account that earns 11.5% compounded continuously. How long will it take for the investment to reach $10,000? So I don't know where you actually find an account that compounds continuously, but we're just going to pretend that it does. Remember, when it's continuously, it's the PERT formula. Oh, excuse me. We'll start with the amount. Amount equals P times E to the RT power, but I call that PERT because it helps me remember. So the final amount is $10,000. The original amount invested is $5,000, and your interest rate's 11.5%, which is 0.115 T. So we've used this formula before. All we're doing now is solving for T, which happens to be up here, instead of typing all of this in and getting this number. So we're going backwards instead of forwards. So the first thing you want to do is get the part with the power by itself. So we want to get the E part alone. So we're going to divide both sides by 5,000, and we end up getting 2 equals E to the 0.115 T power. So remember, when we write these in log form, we end up with natural logs. So for example, I could write this log base E of 2 equals 0.115 T, but log base E is actually natural log. So we would say natural log of 2 equals 0.115 T, which is a little faster, and then divide both sides by 0.115. If you type that in, you get 6.03 years, so T is approximately 6 years. We'll just go ahead and round that off because it's just barely over 6 years. Okay, going down to number 2. I should be able to give you any formula with E in it and give you some information, and you should be able to use it. So you might get formulas that don't look anything like this, but the point is we should know how to deal with equations that have E. Nuclear energy derived from radioactive isotopes can be used to supply power to space vehicles. The output in watts of the radioactive power supply for a certain satellite is given by the function below. How much power will be available at the end of 180 days? So the part that I didn't really explain in here that we normally would with T, this is T days. So for the first part, we're just going to put 180 in. So 40 times E to the negative 0.004 times 180. And using those fancy calculators, you should be able to put all of this in. Just remember, all of this is in the power on the E. Some of us were struggling with that before, so make sure all of that's going into the power. So it comes out about 19.47 something. So we're going to round it off to about 19.5, and it tells us that that is watts. So that's how much power is left after 180 days. Consequently, when you see an equation like this, just like on this problem, your original amount of money goes in front of the E. Down here, even though they don't tell us, since we have this 40 here, that means that we are starting with 40 watts. So even without us telling that, we know that's what that is in the equation. On B, it says, using the same equation as in the last example, how long will it take for the amount of power to be half its strength? So we're starting with 40, and so half its strength would be 20. So half its strength would be 20 watts. So you would have to get the 40 out of the equation to figure that out. So we are going to use that. So you'd have 20 equals 40 times e to the negative 0.004 t. Now we know it's going to be close to 180 days because we had 19 and a half up here. We know it's going to be close, but it won't be exactly the same. So we want to get the e part by itself, so divide by 40. Divide by 40. We're going to get 0.5 equals e to the negative 0.004 t power. I'm going to make the e bigger so it looks more like a power. This eraser doesn't work very well, sorry. 0.5. So if we rewrite this in natural log form, I'm just going to skip to that, you'll have natural log of 0.5 equals negative 0.004 t. So you'd have log base e of 0.5. I just skipped all that, went ahead and wrote it as natural log 5. And then to solve for t, you divide by negative 0.004. So we've solved these equations actually with the e's before, we just haven't done the story problems. And so it comes out 173.3 days. We knew it was going to be close to 180, but not quite. All right, so any equation I give you with e, you should either be able to put the information in and use the formula forwards, or solve for something that's in the power on e going backwards. We've learned how to solve these equations before. We're just wrapping it up with some story problems using some of the formulas that have e in them. Okay, so the next equation, they're giving you a formula, a of t, that's function notation, for the amount at the end of a time period. So this is all one number. If you want to just call it a equals, you can instead of that t. The little a is zeros, the original amount. E is just that number we've been talking about. T is time, might be years or days. We'll have to read it in the problem. And K is a decay or growth constant. Positive K means growth. Negative K is for decay. So it's just going to give us a general formula here. So radium-226, another radioactive isotope, which used to be used for cancer treatment and as an ingredient in fluorescent paint, decomposes radioactively. So this is a little bit like our half-life problems. Its half-life is 1,800 years. That's going to be time. Find the constant K, so that's what we're looking for. You would use in the decay formula for radium. Use 1 gram as the initial amount, so that's going to be a 0. Then determine how much radium-226 would be left after 500 years. So we're going to do two different problems. So let's start with finding the constant K. So they don't tell us how much. I guess they do tell us to use 1 gram as the original amount. And then we're going to look for the constant K, so we're going to use the half-life. So the original amount is 1 gram, and then after the half, so I'm going to write this over here. So the original amount they're telling us to use is 1 gram. And then after 1 half-life, remember half of it decomposes, it's no longer radioactive, we would have half of a gram left. So I'm going to call that 0.5 grams. You could use the fraction 1/2, same thing. Okay, and we know that this happens, it goes from here to here in 1,800 years, which is what they give us up here. So we're going to use all of this to figure out what our constant K is. So 0.5 equals 1 times e to the K times 1,800. So really dividing by 1 is not going to be that useful. We can just think of this as 0.5 equals e to the K times 1,800. Or you could write that as 1,800K if you prefer. Then to solve, we're going to write it in log form. So 0.5 natural log of 0.5 equals K times 1,800. And then to solve for K, we would divide by 1,800. divide by 1800, and we'll get negative 0.000385, blah, blah, blah. It's approximately equal to K. I'm looking at last year's notes, so I don't remember if I rounded that last number or what exactly happened. So you might type that in your calculator and check. So that's the answer to the first question where it says find the constant K. Then it wants to know, determine how much would be left after 500 years. So now that we know what K is, we can write our own formula where the amount is 1 times e to the negative 0.000385 t, where t is our years. So we've basically made a new formula. This is a formula that we could use for radium-226 in all situations. Now that we've created it, it's good. I don't know, in some situations you might want more decimal points, but this is probably good for most things. So in 500 years, we just put 500 up there. And so the 1 really isn't that big a deal. We can type in our calculators e to the negative 0.000385 times 500. Remember, all of that is in the power. If you type that in correctly, you'll get about 0.82 grams. So we started with 1 gram. That's how much is still radioactive. So remember, it gradually changes into something that is not radioactive. Okay, I'm going to move on to number 4. Remember, you can pause the video at any time. So here is number 4. The city planners in Bakersfield, California are studying the current and future needs of the city. The sewage system they have in place now can support 250,000 residents. The current population of the city is 175,000, up from 106,000 10 years ago. Assuming that the population will continue to grow at this rate, when will the sewage system need to be updated? So we're going to use a basic formula just like we had. For a lot of these situations, we can use that number E. So this is our original amount, or I'm sorry, this is the amount afterwards. This is the original amount, which they'll put a little O for original, times E to the KT power. So this is just our basic formula. So we know that the original amount 10 years ago was 106,000. So that's going to be AO. This is how much we have now. That's our amount now. And then we have 10 years ago for T. So what we need to do is find K first and write our own little formula. So we're going to put in these two numbers to figure out kind of this, they call this the growth factor sometimes, that constant. So we're going to use 175,000 here, 106,000 there, e to the k times 10 because it was 10 years. So then we want to solve for the part with e, so you divide by the 106,000 and we'll get about 1.6509 blah blah blah. You would probably want to just keep that number on your calculator. I wouldn't round it off a whole lot. And that equals e times k times 10, or e to the k times 10 power. So then we could natural log that answer. So if you can use that answer feature, it's on your calculator. So you have this number still on your calculator, then push natural log, second, A and S, it's towards the bottom. Anyway, that equals k times 10. And then divide by 10. Divide by 10. And we get about 0.05 for k for the growth factor. So then we can write our own little formula now where we have the amount equals sorry, my brain just stopped for a second. So the amount, actually I don't want to do that. We could write our little formula, but I'm going to run out of space. I'm looking at my notes from last year. So it asks, when will the sewage system need to be updated? So we're going to switch this a little bit. The one that's in place now can support 250,000. So that's going to become my new amount that we will have at some future year, and then we're going to change what it is now to the original amount. We don't need this one anymore. And we're going to solve. So we're going to use basically the same setup, but now I'm going to put in 250,000 equals 175,000, going off onto my notebook paper here, e to the 0.05 t, that constant we just found. So you can use the same setup. It's the same formula that we have here, so I don't need to rewrite it. We're just going to change, now this is the original number, and we're looking for when it's going to hit this number, which will end up being the final number. I realize I'm not explaining this very well. Hopefully you're tracking. Divide by 175,000, divide by 175,000. We get something like 1.4286, blah, blah, blah. Keep that number on your calculator. Don't round it off a whole lot. And then e to the 0.05 t. And then to solve it, we'll have natural log 1.4286 will equal 0.05 t. Divide by 0.05, divide by 0.05. And we end up with about 7.1 years, which I'm going to write over here, 7.1 years. Sorry I didn't space this very well. So we use the same basic formula that's over here both times. We just changed from the original 10 years ago to now. And then over here we went from now to sometime in the future to figure out how long that's going to be. So in 7.1 years, we'll have reached maximum capacity for the sewer. 250,000 people, they'll need to update it, or things will get very stinky. Okay, moving on to part B. How many people will this new system have to accommodate for the system to last 15 years before being replaced? So you've reached 250,000. How many people will this new system have to accommodate for the system to last 15? Okay, so if you want to update it and you want it to last 15 years, we got to see where it's going to be from now. So now the new number that we have is 250,000. So we've reached 250,000 in 7.1 years. Now they're okay. So if we upgrade it and we want it to last 15 years, how many people does it need to support? So we can just put in the 15 years and make a new formula. So here's our new starting point. We're putting in 15 years and we'll figure out how many people this can support. So if you type all that in, it's about 529,000, and I did round that off quite a bit. So check out what that actually is on the calculator. I think I rounded some people off here just to make it a nice round number. All right, number 5. A major highway was constructed 5 years ago to accommodate a population of up to 40,000 commuters. It was estimated that the commuter population at the time was about 25,000. Today there are 31,000 cars commuting on the highway each day. Similar issue, except it's a highway instead of a sewer. Still stinky, just stinky in a different way. So we're going to use the same basic setup on our formula. We're just going to start with where we are right now and where we started with. So the commuter population in the beginning was 25,000. And that would be times E. We don't know what K is yet. We're going to find that in a second. And then that'll be times, it says it was 5 years ago. So the time was 5. And now there are 31,000 cars. So it was 25,000 5 years ago. Now we have 31,000 cars. We can use that information since we have a time frame to figure out K, and then we can use K to do the next part. So divide by 25,000. We are solving for K. That's going to give us approximately 1.24 something 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 or I don't remember, maybe that's all it is 1.24. I don't remember. And then that equals k times 5. We'll solve for k by dividing by 5. So whatever that decimal was that you hopefully did on your calculator, keep that, divide it by 5, and then according to my notes, that comes out to be about 0.043. So now we can use that to answer this question. If the commuter population continues to grow at this rate, when will the highway need to be upgraded again? So right now it will hold up to 40,000 people. So we're going to make 40,000 the new number in the future. Currently we have 31,000, and then we'll use e to the 0.043t, and we're going to solve for time. So divide by 31,000. We get about 1.29 e to the 0.043t. Same thing we've been doing. Natural log of 1.29 equals 0.043t. You can think of just putting a natural log on each side, getting rid of this e showing up on that side. Divide by 0.043. And we get about 6 years. So they'll have to replace it in about 6 years. And then a similar part B to the last question. How many commuters will the upgraded highway have to accommodate to meet the demand for an additional 10 years? So now we're starting at this ending point. We're up at 40,000. And we know that that constant for the growth is 0.043. And now we're going to figure out how many people will we have in 10 years. So we're getting that final amount. Type all of that in, round it off, because really we've gotten rid of some significant digits in there, so we're not going to have that many significant digits on the answer. Maybe about 61,500 people if we round that off to the nearest 100 people. All right, I realize this went fast. Go back and watch these again if you need to. Good luck.